This is part 3 of the combined power, heating and cooling feasibility analysis with the RETScreen Expert software. In this video, we will add to our previous combined heat and power analysis a cooling load as well as the required cooling equipment. We will also propose a new fuel and an intermediate power system. Before starting this demo, we have downloaded a built-in example using the Virtual Energy Analyzer. It is a combined heat and power system for an apartment building located this time in a different city, Thunder Bay, Ontario. In the energy sheet, we have previously adjusted the electricity and fuel costs to reflect the current rate for our location. The location of Thunder Bay was chosen because of the proximity of alternative fuels such as biomass and agricultural waste. This will give us more opportunities for the selection of a cleaner fuel when we will add an additional power system to our installation. Before we start our analysis, I would like to verify the overall efficiency of my cogeneration system. This value could be found into the operating strategy section. Our cogeneration system has an efficiency of 67.7. We will compare this value with the value of the trigeneration system later during the demo. Also, I would like to verify the financial viability of the project. Let's remember that the simple payback is 9.6 years and the IRR is 14.6%. As mentioned earlier, we are going to start this demo with the inclusion of a cooling equipment to our combined heating and power system. The combination of power, heating and cooling is often called trigeneration. In our example, an absorption chiller that uses thermal energy available from the heat recovery system is proposed. The first step will be to modify our system selection. I will click on the cooling icon in order to add cooling to my analysis. Automatically, I will see a different system diagram. The left menu in the top ribbon will also be modified. The system diagram includes cooling. However, the cooling seems to be provided by a portion of the electricity generated by the power equipment. It probably assumes that a conventional compressor is being used. I will click on Cooling Equipment in order to modify that default selection. I will select Absorption instead of Compressor for the base load cooling system and return to the system selection to observe my diagram. Now I see that my cooling system is fed with thermal energy. The VA already completed the heating load sections for me. We are going to assume that everything has been done correctly. Note that the heating load for building has been set using the climate data from the location sheet and the building heating load chart available in the online manual. The cooling load section is almost identical to the heating load section. First, I will indicate that my system consists of a single building and that I have space cooling only. No process load for now. I will enter the cooled floor area, 45,000 square meters. Select the fuel type. Remember that we are defining here our base case cooling system, so electricity will be selected. I will estimate the seasonal coefficient of performance for my conventional compressor to 4. My cooling load in watt per square meter have already been estimated based on the cooling design temperature for Thunder Bay and using the chart available in the manual, assuming a medium insulation for my building. I will keep this value. By using the information from the form and the climate database, the model will estimate the peak load in kilowatt and the cooling energy in megawatt hour. The detailed methodology used to perform these calculations is explained in the section 2 of the RETScreen e-textbook. Based on the calculation above, the model is also calculating the electricity consumption for cooling. Because the value may be known by the user from utility bill, an iterative method could be used to adjust the cooling load of the building derived from the curve until a reasonable match with the utility bills is obtained. For instance, if the building manager knows that the electricity consumption for cooling is just over 425 megawatt-hour per year, the cooling load could be modified from 38.7 to 39.3 to obtain this value. In the power load and load characteristics section, for base case, we could observe that the monthly cooling average load column have been added, calculated from the previous section. Note that the power gross average, which is usually retrieved from the utility bills, should now include the cooling load. I will rapidly modify that column. Remember that the example downloaded from the VEA did not include cooling. The power net average represents the power load without cooling. On the system load characteristic chart, you can now observe the blue curve, which represents the cooling load, and you could also see the power load curve going up during the cooling season. In the bottom section, reserved for the proposed case, we can now see that the software is warning us that there is something missing. If I bring my mouse over the icon, the message says that I should check the cooling equipment section. Since I did not define my cooling equipment yet, it seems that the calculation in the above section cannot be performed. It makes sense. I will complete that section and return into the previous section later. I am curious to see the impact of adding an absorption chiller on my load profile. I will click on the monthly graph from the ribbon to be able to observe it live as I'm entering data. My peak cooling load being almost 1,800 kilowatt, I will propose a system that provides all the energy that I need. Another warning message is telling me that I need to provide the coefficient of performance of the absorption chiller. Since I am not familiar with this value, I will use the manual to get an approximation. I should expect a performance of 0.7 with the two-stage absorption chiller. I can now observe that my load characteristic graph for the proposed case has a different profile than the base case scenario. The power load is flatter, and I could now detect the cooling season from my heating load, since the absorption chiller is driven with thermal energy. Only 2 cells are required to complete this section. I need to enter the cost of my absorption chiller. I will use the cost database to evaluate the cost. A peak load cooling system is not required here, since 100% of my cooling energy will be provided by the base case load cooling equipment. I will return to the previous section to visualize the result. The proposed case section is now giving all the information that I need. The power load for cooling is now 0, eliminating the peak of the cooling season, which is an advantage because we are accomplishing peak shaving. The column named Heat for cooling is showing the thermal energy required to run our absorption chiller. Let's now return to step 3, equipment. We are going to leave our power equipment unchanged. Note that the power system of 200 kilowatt does not allow us to export electricity to the grid. All the energy will be consumed on site. In the operating strategy section, we could conclude that adding cooling to our system raised our overall efficiency from 67.7% to 72%. In the Step 4 System Characteristics section, I could rapidly see that a warning message is telling me that the peak heating load is not met. In fact, the capacity of my boiler needs to be verified. In this case, the suggested capacity of the peak load boiler is equal to the peak heating load capacity. Why is that? I would suspect that this value would be equal to the peak load minus the heating capacity of the gas turbine. It is because the availability of the gas turbine is set to 95%, meaning that the heat recovered from the gas turbine is not going to be always available. and the boiler is delivering the energy during that time. If I set the availability to 100%, then the suggested value will change. I will assume that the existing boiler could cover the peak heating and change the capacity. Scrolling down, I could now see that a new section for cooling has been added and observed the system design graph. Cooling is also presented in the system summary. The financial profile of this new project is not as good as the cogeneration project. The simple payback is very long, the internal rate of return and the net present value are negative. Let's now go back to the cooling equipment section. In that section, we enter the cost for the cooling system. We have to be well aware that, in some cases, the incremental initial cost of the equipment could be required. If the existing equipment for cooling is perfectly fine, but you want to replace with a new system, the value entered is correct. However, if cooling equipment did not exist before and a new cooling system is being installed, then the incremental cost is needed, which is the difference between the proposed system, the absorption chiller, and the conventional system from the base case, which is a compressor. This is the same situation when the conventional system needs to be replaced. The incremental cost needs to be considered. We will now modify the value to verify the impact. This will slightly improve the financial viability. If we now observe the impact of this project on the environment, we will discover that there is no emission reduction. The project increases greenhouse gas emission. Let's now propose a cleaner fuel. Since this project is located in Thunder Bay, at proximity to alternative fuels such as biomass and agricultural waste, we will assume that it is possible to acquire some waste at a very good price. In some cases, it may be free, since handling waste could become a burden for the farm owner. First, we will need to return to the electricity and fuels section to add a new fuel. Biogas is included into our database of fuel. We could compare the heating value of biogas versus natural gas. We will see into part 5 how we could also create our own biogas fuel using the biogas option located into the ribbon. We will select biogas and keep the cost to 0 for now. One way of including this new fuel would be to select multiple fuels in the power system form. You could then add the new fuel and decide which of the two fuels will be used, either on a monthly basis or as a percentage. In this case, we could verify that the equipment could handle a variety of fuels. Another way of looking at the situation would be to create a second power system. By clicking on Power Equipment, a power system number 2 could be added. We will create a reciprocating engine. For now, the system will be set as the intermediate load into the left menu, but we will have the possibility to modify this setting later into the operating strategy section. Before completing the new form, I will click on System Design Graph, included in the Options section of the ribbon. This will allow me to see the impact of the changes on the overall system. I will now rapidly complete the new form. The capacity is 200 kilowatt. Fuel type is biogas. Minimum capacity 40%. Availability 95%. Heat rate could be obtained using a chart into the online manual. 30,000 seems to be a good estimate. And heat recovery efficiency then could be 60%. I could now read from the design graph that almost 100% of the electricity consumed by my facility will be generated on site. More than 40% of the heating energy required will be met using heat recovery from the power systems. For the initial cost, I am using the cost database, which is proposing a cost of $5,300 per kilowatt. I assume here that it contains all the equipment to convert the waste material into biogas through an anaerobic digestion. I will also include the O&M cost using the cost database. I am now very curious to start doing some optimization to find the most interesting scenario. This analysis will be performed using the two drop-down lists located at the bottom of the operating strategy section. The user could select which system is the base load and which system is the intermediate load. The user could also choose between the three proposed operating strategies. Note that no matter what you select as operating strategy, the model always assumes that the base load power system operates at full capacity. Even though it would be useful to observe how the operating profit vary based on the selection, it is only showing the result of the intermediate load operation. Also, it's not taking into account the initial cost of the project, the O&M cost, and the financing. I will click on the dashboard in the ribbon in order to access the financial information each time I change my operating strategy. I will select in the vertical view the financial viability table and the cumulative cash flow graph. It seems that we are now looking at a very interesting project, no matter my selection, but the most financial viable option will be full power capacity output. We also have to remember here that we assume a rate of 0 for the agricultural waste. I would suggest to vary the cost of the fuel in order to verify how much I'm willing to pay for that fuel in order to still get a good financial profile. If we now return to the greenhouse gas analysis, we could observe that this new scenario offers a better result. We are now reducing greenhouse gas emissions.